All right, everybody, welcome to today's webcast with Brian Fehrman. We're going to be doing some AI fun stuff today, honestly. It's always fun when it comes to AI. Brian, we're so excited to have you here to share your time and your knowledge with us. I'm going to go ahead and head to the backstage so you can go ahead and get started. And I hope you all have fun. Good luck and see you in a little bit.
All right, sounds good. Thank you, Zach. Let's do this. Before I get started, though, I want to go ahead and just do a quick plug for a podcast, a weekly podcast that myself and Bronwyn and Derek Banks and Joff Thayer and whoever else happens to join in have been doing. We try to put out a new episode each week. It is available on YouTube under at AI Security Ops. So if you are interested in learning about the latest AI cybersecurity news, our takes on various topics, as well as insights, and even tech demos that we throw in. We also get on guests from time to time. We had Daniel Miessler on not too long ago, so that episode is up. But if you are interested in learning about AI things, they do want to go ahead and point you to there. So, like, subscribe, and whatever all those other things are. But let's get to it for the presentation today, which is going to be defeating AI malware detection with AI. I am Brian Fehrman. You can call me Dr. Brian if you want to, or just Brian if you don't. That's cool. This work was done in conjunction with a couple other people, Dr. Francis Akua and Dr. Randy Hoover from South Dakota Mines. But to kind of peel back the mask on the Scooby-Doo villain, if you will, this is actually a summary of a larger body of work that I did for my dissertation, which was investigating machine learning VBA macro analysis using machine learning in a constrained environment. However, I think that our content community people would have laughed at me if I sent over that title, so we went with a shorter one that's a little bit catchier. I do want to throw out some disclaimers here, though. First is that I don't have anything against Microsoft Defender. I think it's actually a really cool product, but it's just ubiquitous and it's free and it's available, and it's something that a lot of people run into. I did reach out to Microsoft about this work just to get approval for them before I presented any results or made any claims, because they have a lot of money and a lot of lawyers, and so I don't want to irritate them. But they actually were really cool about it. They expressed some interest in the work. They gave approval for it for being discussed, presented, and they even gave me feedback on it, which was wonderful. They were like, hey, send over some of the papers you're looking at submitting. And they actually were like, okay, yeah, this is cool, but you could look at this. And just to clarify, this is actually, this. And they were super cool about it. I was surprised. I was honestly expecting to get crickets and then a cease and desist, but that didn't happen. They were cool. I also want to mention that, as I said, this work was originally presented as part of a PhD dissertation. So read that as this is research. It is more of a theoretical and an academic exercise that can form the basis or foundation for future work. That doesn't mean that the things are meaningless here, but just realize that you're not necessarily going to be able to immediately take these things and be off and running and have success. Understand that this is more about the concepts and the approach than a final product. And this is also heavily summarized. Defender was targeted in an offline mode just so that I could achieve like a consistency for proof of concept research. So keep that in mind as we're going through here. And also understand that this is about a year old now, but the concepts still apply generally when we're talking about AI-based classifiers. And so that's another thing to keep in mind, is that here, when we're saying AI, we are talking about classifiers, not LLMs that everyone is familiar with. And also understand that we've only got 60 minutes, and so I'm going to have to gloss over some things. And so I do expect some confusion, and that's okay. Now, about me. Sit while I talk about myself for the next 5 minutes, which I'm not going to do. It's a pet peeve of mine. We'll just move on. So let's go ahead and introduce this. Phishing remains a very popular tactic in social engineering. There is no doubt about that. And we certainly still see Microsoft Office files are one vehicle for delivering malware into environments. And Visual Basic for Applications, or VBA macros, are one method for code execution. Now, yes, within recent years, Microsoft have helped to lock that down a little bit more to make it more difficult to execute macros, but it doesn't mean they're completely gone, which doesn't mean that this work is absolutely worthless. More and more, though, security vendors are turning towards machine learning as defense mechanism. This is actually something that's been around for a while. Machine learning being implemented in the defense products is something that was popular long before things like ChatGPT became popular. I remember at DerbyCon and other events of the vendors coming in and being like, hey, we've got AI. And I'm like, okay, cool. What does that mean? Well, how are you using it? And they're like, I don't know, AI. Like, okay, cool. Well, but you need to understand, though, that regardless of what the vendors might say, machine learning is not a bulletproof solution to solve all problems. That is just not the case. Sure, it can detect and classify things that it has not seen before, but that doesn't mean that it is going to be able to detect everything that is new and that it hasn't seen before. That's just not how it works. And so, what are some of the ways that we can assess potential vulnerabilities within VBA classifier models? In particular, as I mentioned, Microsoft Defender. It is included for free and enabled by default since Vista. There might be people on here who actually don't even remember Vista. It's something that we just don't talk about. So if it wasn't, it wasn't a thing when before you're born, whatever, you might not have even heard of it. So we'll just pretend that it never happened. But Defender, what it is it uses a mixture of signature, static, and dynamic analysis when it is trying to determine whether or not something is malware. And it actually uses machine learning as part of that analysis. They make that very explicit if you go around on their websites and read their different documents. And they actually tell you kind of a mix of what they use, but we're not going to get into that here. And the way it'll work is that they do have local models that will perform analysis locally first to try to determine if a sample is malicious or not. And if they can't get a definitive answer, they will upload it to the cloud if they need to. So that brings us to what were the research questions when I was going through this. First is that given limited computing power and training data, are there techniques that can be used to help predict how Defender will classify a particular macro sample? So that limited computing power and training data are key because Microsoft, they have a ton of money. They have a lot of resources. They have a lot of computing power. They also have access to a ton of training data. And that's why them and others like them, such as Meta, Google, who have been hoovering up data for many years now, certainly had an edge when it came to the AI game, or currently have. They were able to quickly position themselves as big players within this new AI boom because they had the data. Data is the oil, that is the precious material when it comes to AI and machine learning. Getting good data and getting lots of it is still a difficult problem, and good quality data. So they were positioned well for that. I don't have access to that. How can we solve that? Next is there a subset of features that can be modified to reliably change the classification of at least some macro samples while still maintaining the functionality of the macros? So here's the game plan. It was to collect and clean up VBA samples from the internet, then use Defender to classify these samples as malicious or benign, then extract features out of the VBA samples that I could use for machine learning, and then build my own surrogate model to imitate or mimic or replicate Defender's functionality when it came to classifying VBA samples that I would feed to it. With the idea being that this is much faster to be able to use my own surrogate models where I can feed it features rather than needing to feed it entire code samples. And actually in my testing, I found that this was about 60 times faster to use once the model is built versus trying to keep sending code samples to Defender and getting answers back. Then I want to use the findings from what is called feature space, which we'll talk about more later, to guide the modification of VBA code files. So I'm figuring out modifications to make in feature space first, and then I go and I implement those changes within the actual code files themselves. Then I want to take the modified files, test them against Defender, and determine the level of evasion and how well my surrogate model has performed. Which brings us to model extraction attacks. So the idea of a model extraction attack is that you have a target model. You have someone who has already trained a model on a vast amount of data, and you want to replicate the functionality of that model. So one of the ways you can go about it is basically almost like a brute force approach. So you can send data to the model, and it will give you an output, some kind of a classification or some kind of data back. You then take that label and the data that you gave to achieve that label, and you take all those different queries you put through, and then you use those to train your own local model to try to replicate the functionality of the target model. This is definitely a problem within the industry still. There is speculation that that's basically what DeepSeek did, something similar to this in order to replicate some of the other models that were out there, is this model extraction type attacks. But we can use it for other purposes, such as here, which is to allow for iterating through in a much faster manner through feature space with our own local model versus using Defender. And then we can use that also to help us determine where are the classifications and decision boundaries used by our target model so that we can figure out how do we modify things to get around those decision boundaries. So the first step was to collect data. And through various sources such as VirusTotal, VirusShare, and Common Crawl, with VirusShare being actually the best source for getting VBA files, I got in contact with the person who runs it, and they were nice enough to help me out and just give me like gigabytes worth of files out of there, which was absolutely wonderful. Common Crawl was great for trying to find benign samples. But after going through a process of cleaning all those VBAs, such as removing duplicates, removing files that were too large or too small, ended up with about 14,000 files. Other part of the cleaning was to strip macros out of the documents because I don't want classification to occur based upon, say, like images or text within the documents. I just want the macros. That's the main thing I want. Other steps such as removing out comments because classifiers do put in signature rules that are just, they'll look for certain comments within a code such as PowerShell and VBA in this case. So there were a couple other cleaning steps, but we don't need to talk about those here. So then we move on to the initial file classification, which is basically we're going to have Defender state whether or not a macro is malicious or benign. And this is actually one of the things that the people from Microsoft corrected me on. They said, no, it doesn't mean that it's benign. What it means is that it's not detected. So they're not saying that it's good. They're just saying that they can't say that it's malicious, which I get it, fair point, but not detected is a little bit, it's a little bit wordier than just saying benign, right? So just know that when I say benign in this context, what I mean is not detected. It was not detected as malicious. And again, I did put Defender in an offline mode to allow for consistency because otherwise the results are all over the place. You can give it one set of samples and get a certain set of classifications back. You give it that exact same set, literally, I mean, within a minute, and you can get different classifications back. And that makes research extremely hard to kind of narrow things down, at least for this initial proof of concept work. The other thing to keep in mind is that Defender doesn't really seem to scan VBA in just plain text format, at least not when I was playing around with this. What you need to do instead is you need to reform this into Microsoft's proprietary binary format, which you'll usually see like the VBA project.bin file, which is usually where that information resides. And that's part of what makes the process so slow to interact directly with Defender and part of the motivation for doing a model extraction attack to create your own surrogate model. So after sending those macros through Defender, I get out classifications. So out of about 14,000 macros that I had total, we had about 4,000 malicious and about 10,000 benign or not detected. So about a 3-to-1 ratio of benign to malicious macros. Next step. So we got to figure out features. So what are features? Well, features in the terms of machine learning are items that we can use to try to describe something. So if we want to classify something, we have to have features that we can use where we have values for those features so that our computer can try to make a determination on what it's looking at. So let's talk about maybe like facial recognition. And you look at me and you might think like, oh, hairstyle, eye color, eyebrow width, complexion, roundness of face, nose size, mouth size, whatever. Those are all features, right? All right. And so when it comes to the VBA, we have to figure out what are the features that we think might be important. Now, Defender, obviously, Microsoft, they don't share out what they're alerting on. They say that they have like literally hundreds of thousands of different features or data points that they look at when they're attempting to make a classification. I don't have access to that. So instead, what I got to think about is if I were to make a classifier for VBA samples, what are things that I would look at from both kind of a semantic perspective in terms of what is it doing and a syntactic perspective of what does it look like? And so using a combination of features that I put in as well as prior work from other people out there, came up with a list of about 1,300 or so. And this is just a very small subset of them to give you an idea of what I'm talking about when I talk about features. which is things like variable names, function names. What are the different strings that are used within the VBA macros? What are the different libraries or events that are being used, such as like auto open, for instance? Line continuation operators, how many of those do we see within a file? Binary operators, such as that concatenation operator with the ampersand, how many times is that present? Things of that nature. These are all different features that we can extract out of a piece of VBA code to help classify it from a machine learning perspective. So the next step then is to actually extract the features out of the VBA code. Now, this is easier said than done. What I turned to here was Roslyn. For some of you who might be familiar with this extraction methodology, you might say, well, why not Antler? Antler is actually a very good choice, and it is something that I looked at later on to the research, but by that point, I was so kind of heavily invested in Roslyn that I just kept with it. But I do think that Antler actually is a little bit better choice if you're going to play around with this yourself, just because it has so many predefined rules that have been put in by the community that is really good at being able to extract features out of various types of code, not just VBA. It's good for lots of different types of code. But what we get with the either one of these is what we're going to build is we're going to build an abstract syntax tree. An abstract syntax tree is basically just breaking code down into its discrete components. And so over here, we have an example of that where we can see, okay, we've got a statement sequence. In this case, it's a while loop. And as part of that while loop, we have a condition. Here are the operators of our while loop. Here are the conditions of it. Let me look around my screen here. There we go. I think it'll sync up. Yep. All right, so we got these variables here, and we're comparing it to a constant, but we also branch within that, and that branch has a condition, and so on and so forth. So we're breaking it down into its discrete components so that we can pull out these different components as features if we need to. You might say, why not use a regular expression? Well, you're not going to have a lot of fun with that. You can certainly get some features out with regular expressions, but the thing is that regular expressions are meant for what are considered regular languages. And VBA in itself is not considered a regular language with all recursive properties and other things that it has going on. You're probably not going to have a very good time extracting, trying to write all the rules to catch every single potential outcome and condition that you can think of to extract it out. That's where things like Roslyn and Antler come in. The thing to understand, though, is so up top I mentioned that this is an open source implementation of a VB.NET and C# compilers. Well, VB.NET is not the same thing as VBA, unfortunately. They do both use the Visual Basic Runtime library, but it's not quite the same. So with a whole lot of trial and error, I was able to extend out Roslyn VB.NET to be able to parse out information from VBA to turn it into an abstract syntax tree. So we got our features out. So next thing is we want to go ahead and start training our model. So we had our classification information from we got from Defender before on which files are benign, which are malicious. We've now extracted features out of those files, and now we need to use those pieces of information to train our own surrogate models. So I tried out a couple different models to see which ones would work best in terms of testing the performance of common models such as deep neural network, k-nearest neighbors, random forest classifier, support vector classifier, and XGBoost. And don't worry, we're going to talk about each and every one of those in the next slides. Next, reinforce the models by taking the samples that I have, making modifications to those samples, and then feeding them back through for training. So I would modify code samples, feed them to Defender, have Defender classify those modified samples, get the classification out, feed it back through the loop. That's kind of a trick that you can use to when you have a small data set, is you basically use existing data to create new data, especially when you're doing these model extraction attacks. It's very, very useful. And then essentially sampled out some files, made modifications to those files, and used those for testing purposes. So let's talk about deep neural network. So essentially what this is over on the left side, you have your input layer, which is basically, this is just going to be your features that you're feeding into the neural network. And then over here, coming in, you have your hidden layers, which are known as fully connected nodes. And basically all that's happening here is you feed data in, just values, just numbers, and these numbers get summed and multiplied, and then they get put through to the next layer where they get summed and they get multiplied, and so on and so forth, where each piece has a certain effect on other pieces of data And then ultimately at the end, you end up with typically some kind of a classification. We're talking about classification algorithms. In terms of large language models, you're going to end up with different tokens that are or probabilities for tokens that are on the outside. But this is really all that's happening underneath. I mean, it is like, I know this is an oversimplification, but it really basically just is adding and multiplying numbers. There is really no magic. There is no I know we can have a whole philosophical debate on sentience and what is consciousness and all that stuff, but I mean, like, I don't really see it here with just adding and multiplying numbers. It's that's really all that's going on underneath, and I think it's important to understand that when we're talking about certain types of AI, is that it's just math. It's just math underneath. So let's talk about the k nearest neighbors algorithm. So the last one, the last model type that we talked about, deep neural networks, that's what's known as a supervised learning algorithm, where basically you have data that has been classified and you train the model based upon that classification. So you know what the training data should be labeled as before you throw it in. K nearest neighbors, though, this is what's called an unsupervised learning algorithm. So basically you have data and you might not know a label for it, and you're going to cluster it together based upon kind of its position in whatever feature space you're in. So here we're in a two-dimensional space because that's easier to visualize, but it could be n-dimensional space, above 3 dimensions. Obviously, we as people, that's not something we can really visualize because it doesn't make sense to us, right? But here we're in a two-dimensional space. And so this algorithm has been run prior, and it's figured out that based upon the position of these items within this space, that some should be squares and some should be triangles. Not like the literal shape, but that's just the representation of what group they're in. So let's say, group A, group B, whatever you want to call them, but here it's just represented as squares and triangles, right? All right, so based upon that, we now have another data point that is in the middle, which is this circle here. And we want to know, is the circle more like the triangles or is it more like the squares? And again, we're not talking about the literal shape. We're talking about the characteristics of it. So now with the k nearest neighbors, k is the number of neighbors that you're going to look at to determine what is this most like. And here, if we choose 3 as the k value for the nearest neighbors, we're going to say this new value is most like the triangles because we have 2 triangles in here and only 1 square. However, we expand that out to k equals 5. And now, it looks more like a square because we've got 3 squares that are within this radius here versus the 2 triangles. So that's kind of the gist of the k nearest neighbors algorithm. Up next, it's my favorite one, which is called the random forest classifier. And as you can probably imagine, a forest is made up of trees, typically, right? So what we have here is we have multiple decision trees that are trained on different subsets of a data set and different features and characteristics from that data set that get kind of picked out with random starting places. And so we go through and we train all these decision trees, which are really at their core, basically just kind of like a bunch of if-else statements is how I put it. So you can be like, if you got an animal classifier, you might be like, does it have legs? Yes or no? And then go left or right down the tree. And okay, does it have 2 legs or 4 legs? And left or right down the tree. And you keep going, basically left or right down this decision tree until you get to the end and it tells you, okay, based upon everything that I've seen so far, it's a cat. But then you have all of these different trees that have all been trained just a little bit differently on the data set. And so you get an output from each of those, and then you can either take a majority vote. So you say that, hey, the majority of the trees in this forest say that it's a cat, or you could take an average approach or say, next up, the support of vector classifier. Now, this is one of the first common use, free use examples, graphs that I found, which honestly, I don't think it's the best one because it's nice, clean separation of data points. But just understand that, like in most cases, you are almost certainly not going to get this clean of a separation in data. That just happens to be the example here. But most problems are not going to be linearly separable like this, and so there are certain trade-offs. But for this particular case, where we do have this nice linearly separable data, what you're basically doing is you are just straight up drawing a decision boundary in between those two groups of data. And so you'd say anything above the line is that's part of the blue circle group. Anything below the line, that's part of the green circle group. But again, remember, these aren't like the literal like shapes and colors. Just fill in the blanks, whatever your favorite things are. And the idea is that we're drawing this decision boundary such that it maximizes the distance, the space between the boundary and the groups on either side of it. Now, again, this is shown in two-dimensional space because that's easiest to conceptualize, but this can actually apply to n-dimensional space where we're talking about doing hyper classes. It doesn't just have to be a two-class problem. You can apply support vector classifiers to multiple classes. So there are a lot of opportunities with this approach. You might also see it too noted as a support vector machine versus a support vector classifier. It's basically the same thing for all intents and purposes. Next, let's talk about extreme gradient boost, or XGBoost as you'll usually see it. Now, this one, I had a really hard time finding a good diagram for this, or even coming up with one myself, because I think it's really hard to visualize. But I think the best way to think about it is it's kind of an extension of the random forest classifier. And really what it is you train up your decision trees like you may have before, but you might make them a little smaller than you did before for the random forest classifier. And when you train those decision trees, you're almost certainly not going to be 100% accurate. You're going to have errors. And with a XGBoost, what you're doing is you're taking those errors from training the decision trees, their smaller decision trees, and you use those errors to help kind of guide the training of new decision trees. So new decision trees are trained based upon the error of old decision trees, and you can keep going on, so on and so forth. I think theoretically, you can get down to basically 0% error, but at that case, you're likely going to be overfitted, is what it's called, meaning that, sure, you can correctly predict a new sample comes in that is careful there about overfitting. But usually if you're going to, for people who are competing in competitions, like data competitions, it's quite likely that usually see that the winners use an XGBoost because you have that static data set. And even though they might not be able to see what the final test data set is, I mean, you submit enough attempts, you're eventually going to be able to infer that information. And so a lot of times you will see that XGBoost and other boosting type algorithms are typically at the top of those competitions. So let's look at the comparison of these models. This is a whole lot of information all in one slide, especially with the kind of the summarized approach that we are taking here. So remember that I had talked about that I had a small training size originally of around, we had about 12,000 samples, and it was about 4,000 were malicious, or 4,000 were malicious, and it was like 10,000 were benign, something like that. So if I strip that down so that I can get a 50-50 split, end up with about 4,000 total samples, 2,000 of each, 2,000 malicious, 2,000 benign. So that's over here on the very left column. So that's basically, consider that the base data set, if you will. And this top number in each row is the accuracy. Percent accurate. And then the number below it is what's called the F1 score, which encompasses a little bit more than accuracy. It takes into account basically ratios of true positive, true negative, false positive, false negative, to give you a better idea of how well this is actually performing. So on the base data set, not so great. But remember that I said that I had a trick for generating additional samples based upon that smaller data set that I started out with. And so you start adding in those additional samples that I'm generating up based upon the samples that I already had, and you can see that performance starts to go up quite a bit. With the best performer being random forest classifier here, where I hit over 90% accuracy, meaning that 90% of the time, when I fed features from a sample, a VBA sample, to my surrogate model, my local model, 90% of the time it would match the prediction that Defender would give for that same sample. That's pretty good. I mean, especially considering that, like I said, Microsoft says that they have literally like hundreds of thousands of features, and who only knows how many data samples they were able to train on. But just using my measly little data set and 1,300 or so features, I was able to come up with about 90% accuracy in terms of matching their predictions. And then over on the right, just showing the distribution. So when you talk about classification, it's good to see, especially binary classification, you want to see the distribution of samples, and you want that distribution to be closer to like a 50-50 split. So here we've got 55,000 benign samples, 45,000 malicious. Now, the reason you want it to be closer to a 50-50 split is because if you got something like a 98-to-1 split, like this row up here, that means if just 100% of the time I say it's benign, that means that 98% of the time I'm going to be right. And that doesn't tell you anything. But once you get closer to this 50-50 split, you want to be, if you can do better than 50% accuracy, that means that your classifier is doing something good. Like, you are getting good results. There is no doubt about it. And a funny side note is, if you have a classifier on a binary classification and you get less than 50% accuracy, well, then at that point, you just want to invert your result, because whatever you say that it is, say it is the other thing, because you're going to be more accurate. So next, we need to talk about the features that we're going to modify. So we've got our local classifier now that's a surrogate model of Defender. Now we want to talk about how are we going to modify files to try to flip them from a malicious classification to a benign classification. And so for this work, I chose a very small subset of features to work on, because modifying features is actually very difficult. And we'll talk about that in a little bit. Basically, some of the low-hanging fruit that I looked for when just getting together this proof of concept is things like length of variable names, entropy of variable names. So basically, how many different types of characters you're using within a name, and the ratio of uppercase to lowercase in variable names. Same thing for function names, and then also basically the size of function bodies within a code sample, which is just the count of lines. So we have our features that we would like to modify. So that's the features, but now we have to find good values for those features. Remember, the feature is the thing where we have, we say lines of code, or lines of code in a function. That's a feature. But 10, that's the value. So we need to determine values for these features when we're attempting to flip Defender's classification from malicious to benign. And that's where we can look towards what are called search algorithms to try to help with this. Now, the idea is that we're going to use these search algorithms to make modifications in feature space. Now, when I talk about feature space, what I'm talking about is that we have our set of features that we've defined, and we've extracted out values for those features. So for each code sample, we have gone through and we have extracted out values for the features that we have defined. And really what this basically looks like is a spreadsheet. Honestly, a lot of times if you go out and you get data sets, it's probably a spreadsheet. I mean, just think of it basically as rows of data in a spreadsheet. That's basically what we can think of for feature space here. And so we want to make modifications within that feature space, because that's fast. That's basically you're just changing numbers in a row. You're changing numbers in a spreadsheet, if you will. That's very fast to do, versus making changes within the code, where you have to actually go through, you have to modify the text within a code file, you have to reform it into the proper format for Defender to analyze and send it off. That's very slow. So we make those modifications in feature space, and since we have our surrogate model, we can just feed those feature values directly to our surrogate model, again, rather than needing to feed code to Defender. But ultimately, once we get good feature values, we will make the modifications in code and then send that code to Defender to test how well we did. So let's talk about the different search algorithms here. We got genetic algorithms, simulated annealing, random search, and constrained brute force. So genetic algorithms, these things are really cool. I first learned about these in undergrad, and I still think that they are one of the neatest things out there. I obviously don't want to get into a conversation about evolution and all that, but let's just say that this is modeled after Charles Darwin's theory of natural evolution. and it can be used for finding good or potentially even optimal values in some problems. And the idea is to try to outperform random searches. So here's the idea of a genetic algorithm, is that you start out with initial population of values. And this population, we will call it, we'll call these chromosomes or individuals, but basically sets of genes. And each individual has its own set of values, and those values correspond to a feature. So remember, we have our features that we looked at, which we'll see again on the next page. We've got values for those. A set of values for features equals an individual. Our population is a set of individuals or chromosomes, however you would like to call it. So after we got our set of chromosomes, we want to check their fitness, which is basically how well did they perform, which in this case is going to be how many samples did we flip from malicious to benign when testing against our surrogate model. Then we choose which chromosomes to keep based upon a couple criteria that we'll talk about. The next step is the cool part, which is crossover, which is basically we are combining traits from the selected chromosomes to create new chromosomes. For all intents and purposes, we are mating the chromosomes to create offspring in a digital sense. And then we repeat the process until some specific criteria is met, such as maybe like number of iterations or specific fitness, or maybe you stop improving, whatever you want. So again, when we're talking about chromosomes here, basically what we have is we have our set of feature values that we are looking to modify, those 7 different features that we want to come up with good values for. So each chromosome is made up of values for those different features. And then we apply constraints, good starting conditions, and also things that make mathematical sense. For instance, upper lowercase ratio, I mean, you have to be between 0 and 1. You can't be outside that because mathematically that does not make sense. The rest are just good ranges that I found to kind of play around with as starting ranges. So the idea then is that for each chromosome that we have, we're going to go through and we're going to apply those values across every single data sample that we have, remembering that each data sample that we have actually has about 1,300 features to it. And we're going to change the value of 7 of those features in there. And we're going to change those based upon whatever chromosome we have. So we take a chromosome, we apply that across all of the samples. We then send those modified samples to our surrogate model in feature space. It will then give us a prediction saying that like, hey, based upon these values, I think it's malicious or benign. And so what we're looking for is we want to see the most flipped from malicious to benign because all these samples started out malicious. So we want to see them, as many as possible, being flipped to benign. And so that fitness is the percentage of the number that we flipped. And once we achieve a new top fitness, we will save those feature values from that chromosome and potentially use that at the end. So how do we do selection in this case? So I use what's called truncation-based selection, which means that in this case, I chose the top 30% of the fittest chromosomes, if you will, the ones that perform best in flipping samples from malicious to benign when looking at our surrogate model. I did, though, use what's called the immigrant method, which is that at each iteration, I introduce 2 completely new chromosomes into the pool. And what this does is it prevents your gene pool from stagnating because you could end up in what's called a local minimum. Basically, you stop making progress, even though there might be a better solution because to give it a real world analog, I mean, basically like inbreeding, you're not getting that gene variety into the pool. And so you introduce completely new genes into the pool, and that way you can kind of keep the changes going the best that you can. Next, we get to the crossover stage. So basically what this is we have our set of genes that we have selected to keep based upon fitness and also the immigrant method. And we randomly select 2 chromosomes and then we cross them over. And so for each case here, if we have 2 chromosomes, we end up with 2 children that are also new chromosomes. And for each feature value, there's a 50% chance that it'll keep the gene from one parent or 50% chance it'll get the other. And then we go through until doing this combination until we have reached the original population size. Now, in this case, I did introduce the concept of elitism, which is I always keep the top 2 chromosomes as is because I don't want performance to degrade. If I have a good solution, I don't want to lose that solution. I don't want to go backwards. I want to go forwards. Then there's also the concept of mutation, which is basically for each value that we have, when we go through that crossover stage, there's a 2% chance that a value will be mutated. And if it is selected for mutation, then we mutate it based upon a random value between 0.5 and 1.5, excluding 1, because we do want it to actually change. But that gives us a little bit more variety. And then we have to clip values to be within an acceptable range. And of course, the elitist children, if you will, are excluded from this because we don't want to mess with success. So here's a general flow chart that I'm sure is mind-numbing to look at in PowerPoint presentation here. But basically, we have over on the left, we have our feature space. Over on the right, we have our code space. And over on the left, we are feeding in extracted VBA feature values. We replace these values with chromosome values. For each of our samples, we feed them through the surrogate model. We get out a fitness score based upon how many samples we flip from malicious to benign. We go through all those steps of mutation, selection, combination, mutation, all that. Go through until we reach our number of iterations. And then once we're done with that, we take our best performing chromosome, the best values that we got, and we use that to guide modification of VBA code files in code space. So we're actually modifying the code files, which we then feed to Defender to see how well it does. Next up, simulated annealing, which is inspired by the process of metallurgy, which is basically the idea that you heat a material and slowly cool it to try to remove out defects and optimize the structure. It can be used on a large complex search basis to potentially find a global maximum. I'm going to work through this a little quicker so we don't run out of time. So we'll go to 1.75 speed instead of 1.5 speed. So with simulated annealing, we'll iteratively explore a solution space where basically we look at the neighboring space of the current solution and consider if that could be our new solution based upon a probability that's dependent on a few different parameters, such as objective function, temperature parameters, and a few other things. One of the cool things, though, with simulated annealing is that we have an ability to accept a worse solution, meaning that we can escape out of a local optima. So it's kind of the same idea as that immigrant method within the genetic algorithm, that we can introduce things that might not be good, but it might help to kick us out of a local minimum or local optima, however you want to call it, to work towards a better solution. So Python actually has a library for this, which was great. I just kept most of the defaults in place. I disabled the local search parameter, which can end up taking up a lot of time if you don't do that, because basically let's just say it'll get very granular. And so I disabled that to give a little bit better control of the number of iterations, because I do want a fair comparison amongst these algorithms. And I capped out the iteration at 5,000 because I didn't show all the parameters for the genetic algorithm, but with the genetic algorithm, we ended up with about 5,000 different things that we tried. So that's what I capped simulated annealing at to make it a fair comparison. Fitness functions, same as the genetic algorithm, which is basically of these chromosomes, how many flip these samples from malicious to benign, and of course the same surrogate model. And the flow looks generally the same here. So again, we've got our extracted VBA feature values that we're feeding in. We are replacing those values with values from the simulated annealing process using our surrogate model to classify them to give us a fitness score, which we will then use to progress within the simulated annealing process. Once you've reached the number of iterations, take our best solution and then use that to guide the modification of actual VBA code files that we can then send to Defender over in code space. So next up is the constrained brute force search, which is essentially come up with sets of feature values. I tried to basically cover a spread of what seemed like reasonable values to me, or in the case of the uppercase lowercase ratio, what makes mathematical sense, and trying to kind of hit the different spots in that space. And the idea is that with the brute force is we take literally just all combinations of these numbers that we can. So the numbers that we have here, these were chosen to be able to get to about the same number of tries, we'll say, as we saw with the other approaches. And so in that case, as I said, we had about 5,000 tries with simulated annealing and with the genetic algorithm. So we want something similar here. With the way the numbers worked out, 4,900 is the closest I could get to 5,000, but close enough. We'll see how it does. So then the idea is that we take the generated combinations and use those to replace the corresponding feature values in feature space. And same old story as before, which is we are feeding that to our surrogate model. We get out the fitness score and we use the best performing values to modify our VBA code. samples, test it against Defender, and see how we did. Next up is the random generation approach, which is that, okay, so we've got these fancy search algorithms. We've got even the brute force algorithm. What if we just randomly pick numbers? What if we just randomly pick values out of a certain space? So we don't have literally any guidance other than uppercase and lowercase constraints. Can we outperform those other methods, which are called stochastic search methods, at least for simulated annealing and the genetic algorithms? Because if we can just randomly pick values, and if we pick enough random values and we end up with a better solution, well, I mean, there's really no point in using all that other like fancy pants stuff. I can generate up a bunch of random numbers faster than I can run through a genetic algorithm or a simulated annealing algorithm. So in this case, it just had Python generate up about 5,000 chromosomes so that we can test those random values against our ones that we found through stochastic search methods and the brute force method. And of course, flow is probably looking pretty familiar by this point, which is we take our extracted values in feature space, feed them into our classifier, get out a fitness score, use that to guide our modification in actual code space. So next up, let's look at the results for this. So each of the methods was run 10 different times so that we could get a better idea of how well these are actually performing against one another, because you get one result. I mean, that doesn't, it's not very conclusive, but you run it 10 times and you start to see some patterns. So what we have here, what these numbers represent, is they represent the percent of samples that they flipped from malicious to benign when tested against our surrogate model, our random forest classifier. So looking at that top, we can see that on average, simulated annealing flipped 62.44% of samples from malicious to benign, compared to the random search, which was 61.77%. Minor difference, correct. I will admit that. Not a huge difference. However, it is a consistent difference. So consistently across 10 different runs, simulated annealing did outperform the other methods such as genetic algorithm, random search, and brute force. And that's a result. That's interesting to see. And I think that that value would probably, that difference between the methods would probably grow larger on a larger set of samples, as well as if we were modifying a larger number of features. Because remember, we're just modifying 7 of the like roughly 1,300 features or so. And so it's not too surprising that the results are going to be close, but nonetheless, I do say that there is a winner here. Even if it wins by just a little bit each time, it still has won by a little bit. So what do the top values look like? What do the values for that top chromosome look like? So when we're talking about when we need to modify a code file to make it appear to be benign, a VBA sample to appear to be benign, what characteristics are most likely to cause it to look as though it is benign or not detected, if you want to be technical? Well, it likes to see a function line count of about 8. So for on average, it likes to see kind of a little bit shorter functions, that average out to about 8 lines per function. It likes longer function names and variable names, seem to make it more likely to be classified as benign. It also likes to see higher entropy values. So entropies of 6, roughly 6 for both the function name and the variable name are relatively high. So it likes to see a good variety of characters that are used within the identifier names there, which is actually a little bit surprising. And then interestingly enough, it seems to like basically all uppercase letters for function names, but all lowercase letters for variable names. I think that's how I read that. Yep. So now it's time to actually go back from feature space into code space. So we have gotten out our set. So let's recap here. All right. So we built a surrogate model that mimics the classification mechanisms of Defender, at least when Defender is in an offline mode. And we used that surrogate model to help guide us to a set of feature values to target for flipping a VBA sample from being classified as malicious to being classified as benign. But now it is time to actually make those modifications. we need to take those feature values and we need to modify our code sample such that it has those characteristics or mimic those characteristics. So we take out our top performing chromosome, which was what you saw before, which came out of simulated annealing. And then we try to modify the code file to have that same characteristic. So go through modifying variable names, function names, and lengths of the functions themselves, and then send to Defender for reclassification. That's where we come to a real challenge. So extracting features and finding targets is one thing. Modifying code without breaking it is a whole nother thing. So oftentimes when you see examples of adversarial attacks, they'll be called, they're almost always with images and videos. That's because images and videos are just pixels, and especially high resolution ones, you have a lot of pixels to play around with that you can change. And to us, we don't see any difference. And at the end of it, it's still an image. Like, it doesn't need to run. It doesn't need to execute. It just needs to look like a picture. That gives you a lot more freedom in terms of how you can make modifications. When it comes to code, though, that is a whole different problem. And it is a very active area of research because you need to modify the code without breaking the code. And just because you have something that exists in feature space doesn't mean that you can recreate that same thing within code space. It's not necessarily an invertible problem. That's where the real challenge comes in. And that's where there's a lot of difficulty. That's where a lot of time was spent trying to make this happen. And so to make this happen, I used a combination of both Roslyn VB.NET and regular expressions. Now, earlier I mentioned regular expressions weren't good for extracting features, at least not in my opinion. They are okay in some cases for basically making modifications, though. And so I used a combination for making these modifications. And so the goal was to keep the functionality. And so how do I ensure that the VBA files are still functional? Well, at the time when I did this, there wasn't really a good way to, let's say, fully test functionality, recompile, and make sure that everything still worked as it was, especially because you got to remember, these are samples that I got off the internet. So I don't know what they were intended to do to begin with. I don't know what their original intended functionality was. So the best I can really do is take the two approaches that I came up with. One is I create my own VBA files that basically performs a set of non-trivial operations and at the end prints a result, trying to encompass most of the features that VBA code might have that might be available to you, and then print out a result. If that result's the same, then, well, functionally, it's probably equivalent. If it changes, well, something broke. Also, a manual selection of files. You look at code enough. I come from a development background, or computer science background, do a lot of development. You look at enough code, you can get a quick sense of whether or not it's going to work. So how'd we do? Well, so after modifying VBA files, the actual VBA code, and sending them to Defender, using that guidance that we got earlier, found I was able to flip about 66% of them, of the samples that I had. So of the roughly 4,000 samples I was dealing with, I was able to flip, these were all malicious samples, able to flip about 2,500 of them to benign. And the cool thing is that this very closely matched the prediction from our surrogate model. So the surrogate model predicted that 62.5% of these samples would be classified as benign by Defender if they were to have the characteristics that we saw in feature space. In practice, after implementing those changes within code space, we find we got 66.15%. That's pretty close. I think that is really, really cool. Personally, that we have this little surrogate model that, at least for Defender in offline mode, does pretty well at predictions and allows us to iterate through that search space more quickly. So in conclusion, basically what I come up with here is a method for doing some targeted evasion attacks on VBA files with Windows Defender in offline mode. And so we had the surrogate model that we created based upon classification outputs from Defender. We found that RFC model performed the best out of those 5 different models that we tried. Surrogate model allowed us to iterate through feature space to quickly test changes before making the changes in code space, which is very slow. Simulated annealing was the best in that search category. And we found that the performance in the code space very closely matched the predictions from the surrogate model and feature space, which I think was cool. So in conclusion, that slide wasn't supposed to be in there. Just ignore that it was there. I thought I took it out. It's still there, and it's same information. So future work, though, want to get additional VBA samples because more data is always better. Yeah. Improve the modification pipeline because I want to be able to modify more features. I think if you can modify more features, you can probably get better results and more interesting results. Of course, further confirmation that the files are actually maintaining their functionality. And then, of course, put Defender in an online mode to test how it performs in that situation. So, of course, want to give a huge thanks to Black Hills Information Security for helping to support my work, and especially the PhD process. So huge thanks to John and Erica and everyone who works at Black Hills as well to help make this happen. Love all of you. This is great. Huge shout out. Also, shout out to South Dakota Governor's Center for Disruption of the Illicit Cyber Economy, because this was actually part of a project that we were working on with them. And then, of course, South Dakota Mines. And so with that, I will wrap it up and also just go ahead and plug this again for those of you who weren't here at the beginning, because we want to let people know that this exists, because a lot of people don't know that this exists yet. And so come check us out. And so I think that's it. I think we're done. I think we can do some questions.
Awesome. Thank you so much, man. Appreciate it.
Yeah.
It's fantastic.
Yeah.
You have one question, and before I forget too, not only can people find more of you on the AI SecOps podcast, you have a workshop coming up September 25th. Could you tell us a little bit more about that workshop?
Yeah, sure. Let me find my window here and see what I'm looking at. Sorry, it's like 80 degrees it's like 81 degrees in my office, so it looks like I'm in a freaking sauna here. So the workshop coming up, it's a collaboration between me, Derek Banks, and Joff Thayer, and we are going to be focusing on attacking AI LLM infrastructure. So we've got some really good foundational knowledge. We talk about the different attacks. I think we mentioned some of the different defenses that are in there. And we actually have an entire CTF that we put together that will be open source. It's actually, I hate to give it away, but if you can look around, you might be able to find it right now. But it's something that you will be able to take and you can play with on your own. So we have, I think, 11 different challenges in there that encompass all the different types of attacks and defenses that we could fit into it. It's centered on or built around open web UI, which is great. And we think a lot of people are really going to enjoy it. For those of you who are interested in really getting your feet wet with attacking and defending AI and LLMs and seeing really how all that works underneath.
Thank you, man. Appreciate that. I'm looking
Yeah.
forward to it.
Yeah.
So one of the questions that I had, I just lost it because I put something in the chat. I'm terrible at names, so I'm not going to try to butcher their names. I'll just say Siri. Was there a reason to try to stack these different implementations that include prevent local optima capabilities? They're saying it's a little unclear whether this part is comparing different approaches and then picking the most performant, successful resulting system, or if you're layering approaches.
Okay, yeah, excellent question. So this was just a comparison. So with both the models and the like the search algorithms, I guess you would call it, in both cases, those were a comparison, not a layering. So I wanted to see, which for these use cases, which ones seem to perform best, rather than just be like, hey, I just picked one and it seems to do well. It's like, well, but there's other ones out there. So how do they do? So it's just a comparison.
Thank you. Security Q, you were asking just now if you get a certificate. You do get a certificate of completion for all the different classes or webcasts that you take here with us.
Yes.
Gregory is asking, how many different offline modes did you test with related to flipping from malicious to benign?
So basically, just when I say offline, what I mean is that I did not allow Defender to communicate back to Microsoft because it is two things. It like basically constantly pulls updates. It pulls a lot of new updates in, and also even though like if you turn off the submit sample thing, it still seemed like it was submitting sometimes and had weird behavior. So really, all I mean by offline is I literally just like it was not allowed to communicate out. So I could ensure that nothing was changing. It was not being updated.
Thank you. Eric's asking if random generation is almost as good. Does that tell us that you could just change one character of a feature value at random and have a similar result?
Potentially, but so you got to remember too is that when I talk about the random selection or the random approach, I randomly generated up 5,000 different sets of the 7 different feature values to try across the samples. So it wasn't just that I randomly selected one value once and it happened to, flip however many. It was a lot of different tries basically that it had going on there. So I mean, could you, flip one and get success? Possibly. I mean, it's possible, but just understand that that's not exactly what happened. It was still trying a lot of different values, but it wasn't like they weren't guiding themselves. There was no, they weren't like really searching. It was just, pick a bunch of values and try them and see if you happen to get one set of values that works well.
Thank you. Before I get to the next question, I'm going to throw this link back in the chat for SurveyMonkey. If y'all don't mind, if you could take a minute or two to fill out the survey, John Strand would really, really appreciate it. I'm giving him a hard time, but we would all actually really appreciate it because it will help us improve. So, if you appreciated the time that Brian spent with you today, please take a moment and fill out that survey. We'd appreciate it. And anonymous attendee is asking, or saying, let's see, making sure that's a question. I don't think it is. Here's one. Can you tell me the platform to practice AI attack and defend techniques?
Yeah, so if you, I guess it depends on exactly what you want to play around with. If you're talking about if you're talking about like the AI LLM stuff, um, there are quite a few different things that are out there. So you've got Lacera is probably one of the biggest one. I know that they just came out with a bunch of new challenge sets that I haven't gotten time to play around with, especially I think they're all like agentic based challenges. So you can check that out. As I said, we'll formally be releasing a CTF that we put together that you can take on your own and play around with and pull it apart as much as you want, which will be out. We'll formally announce it in about 2 weeks here. If you're looking for more of a mix of not just AI or not just LLM based challenges, but you want to look at, say, like classifier type challenges, so more along the lines of stuff that we talked about here, then I know that Crucible Dreadnought challenges are a good place to look at. They've got a pretty good set and mix of challenges where you're trying to also fool like image classifiers and things that aren't just LLM related.
So, Steve's asking, how proficient are you on those keys?
Proficient arm, what? Oh, not very. No, I am. It's yeah, I play around a little bit. I don't know. I just mostly mess around in like minor scales and stuff. Same thing with the guitar over here. I'm not proficient at all. Joff is the keyboard master, and Bo is definitely the guitar master. If you want to chat the music stuff, they're the go-to. These are more of just a hobby and props, honestly.
Forrest, I put the link for the survey in the Zoom stream. And for the questions, if you are on Zoom, there is a Q&A section. You can put your questions in there and we'll try to answer them live if we can. So I'm not sure how much time you have, Brian, but we know we could take a couple more questions probably. So if you want
Yeah.
to ask Brian a question, go ahead and throw them in the chat. We'd appreciate that. And of course, if you want to learn more from Brian and friends, check out his workshop coming up. Put this in the Zoom chat too. There we go. Thought Zoom is exclusively for Zoom has no memes. Zoom's the chat's disabled. We just have the Q&A section enabled so people can ask questions there. And, Miss said they didn't catch the classification level challenges platform you mentioned.
Oh, Dreadnought Crucible or Crucible by Dreadnought. I think Dreadnought's the organization. Crucible is the platform. So they do host CTFs up there, but you can also go and just play around on there. So that would be that's one of the first ones that comes to mind. Anyways, if you're wanting to play around with classifiers, attacking classifiers instead of just yeah, Crucible, not Ansible. Yep. Yeah, instead of just LLMs.
Some, I don't see any other questions coming through.
Cool.
So I think we're good. All right. Awesome. Thank you very much for your time today, Brian. Very much appreciate it. If you guys want to check out what we have coming up at Black Hills next, if you go to this website that I'm going to put in the chat, it's powered by bhis.com. That'll take you to our Zoom Stadium, which will show you all of the different events that we have coming up from our anti-casts, our webcasts, our live trainings as well. And we hope to see you in our next one. Hope you all have a great week and take care, everybody.
Bye,
See you all
everyone.
later.
Thanks.
Thank you again, Brian.
Yeah, thank you.
Kill it with fire, Megan.